Imagine you're trying to predict whether someone clicks an ad. A plain linear model looks at each feature on its own. It scores the user, it scores the ad, it scores the time of day, all separately. But the real signal often lives in the combination. This particular user paired with this particular genre predicts a click, even when neither one alone does much. Factorization machines, from a paper by Steffen Rendle in 2010, were built exactly for that problem. Let me show you how they capture those combinations without drowning in sparse data. To appreciate the trick, look at the two obvious approaches and see exactly why each one falls short in the real world. Start with a plain linear model. It gives every feature its own weight and adds them up. Fast and simple, sure, but treats each feature in complete isolation. It simply cannot express that a user and a genre together means something the two of them apart never do. And in recommendation and click prediction, that joint signal is exactly where the money is. Okay, so just add a weight for every pair of features, right? The trouble is scale. With millions of user and item identifiers, the number of possible pairs explodes into the billions, and your data is painfully sparse. Most exact pairs almost never appear together in the training set, so there's simply nothing to learn each of those weights from. You would be estimating billions of numbers from almost no examples. Factorization machines thread the needle with one genuinely elegant idea. Let me walk you through the model piece by piece. First, give every feature its own small latent vector, exactly like the user and item vectors you would see in matrix factorization. Each identifier, each category, each attribute gets a handful of learned numbers that place it somewhere in a shared hidden space of taste and behavior. Then model the interaction between any two features as the dot product of their vectors. When two features tend to fire together in a meaningful way, the training gently pushes their vectors to align, and that dot product grows large. When they have nothing to do with each other, the vectors stay unrelated and the product stays small. The strength of every pairing falls right out of the geometry. The full prediction then adds a plain linear term for the individual features on top of the sum of all those pairwise dot products. So you keep the simple per feature signal, the part a linear model already gave you, and you layer every learned combination right on top of it in one clean score. Because the vectors are shared across every interaction, the model can estimate how strong a rare pair is by borrowing from related pairs it has seen. That sharing is the whole reason it works so well on sparse data. Now step back for a moment and hold on to the three ideas that really make this model matter in practice. Every feature carries a latent vector. Users, items, context, all of it lives in the same learned space instead of getting an isolated scalar weight. Feature interactions become dot products of those shared vectors, so the model generalizes to combinations it barely saw during training. It learns feature combinations on sparse data, where explicit pair weights fail completely, and thanks to a clever reformulation, it computes all of those interactions in linear time rather than quadratic. Let me leave you with 4 things worth remembering. Factorization machines model the pairwise interactions between features, the combinations that plain linear models simply miss. Every feature gets its own latent vector, and an interaction is just the dot product of a couple of those vectors. Because the vectors are shared across all interactions, the model estimates rare feature pairs by borrowing from related ones, so it shines on sparse data. This idea generalizes matrix factorization to arbitrary features and power systems like DeepFM and ads and recommendation. If you enjoy having these building blocks unpacked in plain language, come explore more at standarity.com.